Welcome to this next video, where our question for today is to design an arbitrary sequence counter. A sequence counter circulates a predefined sequence of states where the next state logic of our design determines the pattern in the sequence. For example, if we need a counter to circulate through the sequence described in this table, then we basically need to construct a combinational circuit with this particular functional table that specifies the desired pattern. So our next step is to draw the arterial level diagrams that specifies this particular pattern here. So we can see that we have a D flip-flop and we're simply saying that, and then we have this is the output of our D flip-flop, this is the input, and we have this to be our input and this to be Q as our output, and we say that we have our output here is Q register, and we're basically saying that when we have 0, 0, our next state logic, which is here, should output 0, 1, 1. So we say that we will feed our output to our next state. Let's say this is our next state, and with this we are able to get so when we have 0, 0, this is going to be our Q next, and we are saying that when our Q register is 0, 0, then we have 0, 0, 1 as our next pattern, which is our Q next, and when we have 0, 1, 1, then we have 1, 1, 0. So we can clearly see that. So this is our clock. We can, and we also have our reset. We can clearly see that we can have this as our select line, and we can have our inputs as our next states as inputs to a max, which looks like this. So this means that, okay, let's also delete this. This means that we are going to have a max, and basically we're going to have our sequence here, which is going to be 0, 0, 0, and then we're going to have 0, 0, it's going to be 0, 1, 1. It's going to be our next, and then we are going to have it like that until we reach 1, 1, 1. Then we go back. So we can say that we have in this particular pattern we have around 5 inputs. Okay, so then this is going to be a Q next, and then we're going to have this be our select. Is going to be our select. So with this, now we can observe our output here. Let's call this our output Q, or rather let's call it yes, let's call our output Q. So now let's write the code for this, and then we will write the code for this particular design, and then we'll also write the code for the test bench. So we define our entity as arbitrary sequence counter, and then we now define our inputs, so now we define our inputs. So we have clock, which is going to be, and then we also have clock, and we have reset, which is input, and they're all STD logic. Then we also have Q, which is going to be our output. And Q is an STD logic vector of size 3 bits, so it's 2 down to 0. Okay. So now we finish with our inputs. Now let's define our architecture. Right. So as normally we're going to divide the circuit into 3 parts, where we have our register logic, and then we are going to have our next state logic, and then we are going to have our output logic. Right. So before we continue, we're going to need to define the signals, which are also 3 bits. So let's just write this here to be 3. This one is going to be also 3. Okay. This is 1. And this is 1. Perfect. So then we move on to, so now let's have our signals. So we do have a Q register, we have Q next, and both of them, they are STD logic. And they are 3 bits long. 3 bits in size. So for our register logic, we have a clock and reset. So let's say our reset is asynchronous, which means it doesn't matter if we have a rising or a falling edge of our clock. We are simply going to reset our output 00 when reset is active high. So we define a process with a sensitivity list of clock and reset. Okay. Great. So we're going to say that if reset is 1, then we're going to say that our Q register is our signal, is going to have 0. Okay. And our if, so this is going to be an if-else statement. Else if we are on a rising edge, of our clock. Then what do? Then this time our Q register is going to have Q next, which means we're going to pass our next state to be the current state. Alright, so we finished with our register logic. Now let's go to the next state logic. And for the next state logic, we said we are going to have a max like this. So what we are simply going to say, we are going to say that our Q next is going to be, so our Q next is going to be 0, 0, is going to be 0, 1 when excuse me. Our Q next is going to be 0, 1. Sorry, it's going to be 0, 0, 1, 1 when our Q register is equals to 0, 0, 0. Else we're going to have it's going to be, so for you to be able to see this, so we have the next one is going to be 1, 1, 0, and then we have 1, 0, 1, and then we have 1, 1, 1. So let's delete this one. So 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, then 1, 1, 1. So this is the pattern that we are going to follow. So we're then going to go to 1, 1, 0 when Q register equals to 0, 1, 1. Else we will have 1, 0, 1 when our Q next equals to 1, 1, 0. Else we're going to go to 1, 1, 1 when Q next equals to, so this actually is supposed to be Q register. when Q register equals to 101. Then else we finish off with now we go back to 000, right? And this is the end of our marks, this one. Okay, great. So we finish our next step logic, simply looks like that. And now we go to our output, really, which is just that we are sending Q, we are sending our Q register to Q. See like that. Okay, so this is the code for our circuit. Now let's write the code for our test bench, so that we'll be able to test this particular circuit we designed. So we will simply have, we will also use the IEEE libraries. .1164. Oh, this always gets me. Alright, great. So let's now define our signals. So before we, okay, let's define our signals, which we can just get them from here. Okay, so let's also define our clock frequencies and where we can say that our clock frequency is an integer, and we can initialize it to 1 microsecond to 1 microsecond. Okay, then our clock period going to be of type time, and this is going to be 1 second divided by clock frequency. I just realized that all this is in the wrong place. And they're all supposed to be defined as constants. All right. So we also need, so we initialize our clock. Let's just initialize our clock right now, so we don't forget the 1. And we can also have another signal that will tell us when the simulation is done. And this one is going to be of type Boolean, and we're going to initialize it as false at the moment. Okay, so now we can have our process. And then we can have our unit under test, and then we can have our clock. So in our clock, we say that the clock will take not clock when clock period after clock period divided by 2. And this happens when simdone equals to false, else we say our clock is 0. Right, so our unit under test is entity work, and then we take the name, and it's in RTL, then we port map, and we are basically taking these ones and then great. So now let's start our process, where the first thing we will probably do is to reset, and we say that reset is going to have 1, which is active high, because our reset is active high, and then we say wait for let's say clock periods. How many clock periods? wait for 2 clock periods. Let's wait for 2 clock periods, and then after that, after our reset, we don't really do anything else, but we can wait. We know that we have around 5 inputs, so we can wait. Well, actually we can wait for first we have to set our reset to, we need to set our reset to 0, and then now we wait for how many? Let's wait for 10 clock periods. It's actually going to be more, but at least we'll be sure that we will observe the entire cycle. So it's times 10. Then after that, we say that our simulation done is going to be set on true. This will stop our clock, and then we say wait. Perfect. So this is the entire test bench. Now let's simulate this in Vivado. So in Vivado, we just create a new project, and then we select the destination to be arbitrary sequence counter folder, and then we name the project is arbitrary sequence. Then we go next, our TL design, then we add file to be this one, arbitrary sequence counter without the test bench, and then we go next. We don't put any constraints, and we select any general purpose, and then we go next, and then we finish. So when here, we need to add our simulator source of simulation. We're going to add a simulation source, and we're going to select our test bench, then we finish, and you can see in our simulator source we have our test bench right here, and in our design source we have our arbitrary sequence counter. So once it finishes, to update, now we can run a simulation. Let's run our simulation now. We run our RTL behavior simulation. Great. So let's get some room here so that we can observe our output, and we click run all, and it was run, so we fit it in. So what we are trying to see is Q, which is our output. So let's change this radix to binary. Great. So we're here, our reset is 1, so everything is 0. And let's first of all see from our table right here, so we can try and see whether we are seeing the right thing. Okay. So we're saying from 0, 0, we're supposed to go to 0, 1, 1, which is what we have. And then from 0, 1, 1, we go to 110, we go to 110, which is what happened, and then from 110 we go to 101, which is what happened, and from 101 we're supposed to go to 111, which is what happened, and then from 111 we're supposed to go to 000, which is what happened, and it repeats itself. It goes back to 011, like that, and like that. So it seems that our design is working exactly as how we programmed it to, and I hope you've been able to learn something from this design, and see you in the next video.